Good morning, everyone. Today we will study the magnetic force. In last lecture, we introduced the magnetic field and we talked about the magnets and the poles of the magnets and how they are attracted toward the magnetic field of the Earth. Today we will study the magnetic force. So, if we bring a wire closer to a magnetic field, and in this wire we have no current, you will see that the wire is not going to be affected. However, once you have a current going through this wire, then you will see the wire will be affected by the external magnetic field. Why? Because magnetic field will only have an effect on charges when they are in motion. If we have a current, if we have charges that are in motion, then we have magnetic force. And how do we calculate this magnetic force? Now, though this magnetic force is unlike the electrostatic, it's not pointing either parallel or anti-parallel to the electrostatic field. The magnetic force is perpendicular on the plane that has the charges and the magnetic field, as we will see later on. So let's first define the relationship that governs the magnetic force. So the magnetic force, which is the Lorentz force here, equals to Q V cross B. So the cross product of two vectors, the velocity of that charge cross the magnetic field, of course, with the scalar being multiplied by the velocity, then the force would be a vector that is perpendicular on the plane of the V and B. So the mathematical representation to this is Q, magnitude of velocity, times the magnitude of the magnetic field, times sine theta, which is the angle between the velocity vector and the magnetic field vector, times n hat. N hat defines the unit vector of the magnetic force, which is perpendicular on the plane that has the velocity and the magnetic field. So we will distinguish here between two cases. The first case is this charge is being positive and negative. So we have two cases. So let's start first with the charge being positive. In this case, if the charge is being positive, then we will use what's called the right hand rule. So what does the right hand rule mean? The right hand rule says that I would be pointing my index finger toward the velocity of the charge. I will be pointing my middle finger toward the magnetic field, and then the thumb will give me the direction of this force. So if in this case, if I have my velocity as the index finger here, this is the index, this is the middle finger, then you will see that the thumb will be pointing, in this case, will be pointing downward. That's why my n hat that I have introduced in the previous slide, in this case would be minus k hat, because the force would be pointing downward in the negative z direction. Again, theta here is the angle between my velocity v and my magnetic field b. So as long as v and b are the same plane of the xy, and based on my right hand rule, where I have the index finger pointing toward the v and the middle finger pointing toward the magnetic field, then the thumb here is pointing downward, which is the direction of the magnetic force. Now, also, we're still at the positive, charge being positive. However, I have flipped now the magnetic field and the velocity. Here I have the velocity is in this direction and the magnetic field here in this direction. If you apply the right hand rule, where this one is the index, this one is the middle finger, then you will see that the force would be pointing upward, and that's why the n hat in this case is k hat as the result. And of course, the sine theta here plays plays a very important role in defining the maximum magnitude of this force. So you can see this force can be maximum if theta is 90 degrees. If theta is less than 90 degrees, then sine theta becomes less than 1. And in this case, as we have explained, n hat would be k hat. So we still hear the same positive. However, I have swapped the magnetic field and the velocity just to show you how is this is going to affect the force. So it depends on the direction of the velocity and the direction of the magnetic field. The direction of the magnetic force will be determined. Now let's move to the negative charge. For the negative charge, here we will be using the left hand rule. Why? Because that sign is going to flip the direction of the force in the opposite direction. So you can either use the right hand rule and flip the direction 180 degrees for the force, or you can use the left hand rule. Both are going to give you the same answer. So now let's look at the left hand rule. Using the left hand this time, again, the velocity is going to be the index finger, the magnetic field is going to be the middle finger, and then the thumb is going to point toward the magnetic force. So if I use my left hand, put your index finger toward the direction of the velocity, your middle finger is the magnetic field, then you will notice that the force would be pointing upward. And that's why we said here the n hat is k hat, which means that the force is pointing in the direction of the positive direction of the z axis. So the right hand rule, we use it for the positive charge. The left hand rule, we use it for the negative charge. This way, things would be easier for you to try. So let's move to the next slide here. We have a special case. The special case here is the angle theta between the velocity and the magnetic field. It doesn't matter what charge is. The theta is 0, and in this case, sine theta would be 0, and this is going to affect the force. The force here would be 0. So what can we conclude from this case? That uh, it doesn't matter what sign is your charge, as long as theta is 0 or 180 degrees. So either the force, either the magnetic field and the velocity are parallel or anti-parallel, this is going to result into a zero magnetic force. Here we have a positive charge, so let's try it. Let's try it. Use your right hand, put your index toward the the velocity v, put your middle finger toward the magnetic field b. You will notice that the magnetic force in this case is pointing upward in the z direction, and that's why my n hat here equals to k hat. This defines the direction of the magnetic force. Let's move on, try the next one. Now here in this case, I have theta becoming 90 degrees. So here, this 90 degrees is going to result into sine theta becomes 1. This is the case where I have a maximum magnetic force, and it will be in the positive z direction. If you use your right hand rule, put the index toward the V, put the middle finger toward the magnetic field, you will see that the thumb is going to point to the direction of the force, and this is going to be in the positive Z axis. Try the negative. This is a negative charge going in this direction, velocity. Here we have 90 degrees, which is basically expecting a maximum magnitude. So if you use your left hand rule, you will see that put your index toward V, middle finger for the B, you will see that the force is going to be pointing downward, which is, in this case, N hat is going to be minus K hat. So let's look at this question. In this question, we have the following. In which case does the force on the particle point down the page? Pointing down the page, meaning pointing this way. So we can see here from case A that the magnetic field is pointing into the page. The charge is a negative charge and pointing to the left. So in this case, if because it's a negative charge, let's use the left hand rule. Point your velocity index toward the velocity. Point the middle finger into the page. You will see that the force is going to be pointing downward. So this one has the force downward. Let's look at B. B, it's a positive charge, so I'll be using my right hand rule. Put the index toward the V, the middle toward the magnetic field. You will see that the force here would be pointing into the page. Case C, I have a positive charge. Put the V into the index. Magnetic field is parallel to the V, which means F here is zero. Right away, once you see the velocity and the magnetic field parallel or anti-parallel, the force is going to be zero. The D case, I have a positive charge. The uh, index toward the V, the magnetic field, the middle finger toward the magnetic field, and then I will see that the force is going to be here in this case pointing upward. So case A is the one that gives me a magnetic force pointing downward. So what is the unit of the magnetic force? The unit of the magnetic force is in Newton, and the magnetic field is Tesla. So what are the properties of this magnetic force? Number one, only moving charges are going to experience the magnetic force. If the charge are stationary, then there will be no magnetic force. As you have seen, the velocity is an important vector toward calculating the force. So as long as they are in motion with in the existence of an external magnetic field, then there is a force. In the case of the velocity is parallel or anti-parallel with a magnetic field, the force is going to be zero. I get maximum magnetic force when I have the angle being 90 degrees between the velocity and the magnetic field. Also, remember that the magnetic force is always perpendicular on the plane that has the velocity and the magnetic field. The direction defines by the charge using either the right hand rule or the left hand rule, but it is always perpendicular on the plane that has the velocity and the magnetic field. So The direction again is defined by the sign of the charge, either perpendicular up or perpendicular down. That depends on the sign of the charge. And of course, with respect to the velocity and the magnetic field directions. So, question: an electron moves perpendicular to a magnetic force as shown. What is the direction of the magnetic field? So we have here a negative charge. We can use the left hand rule to find the direction of the magnetic field. You just need to point your index toward the velocity, which is in this case, it is pointing downward, and then point your thumb toward the force. You can see that the magnetic field is pointing into the page. So this is going to be the magnetic field. So here it is into the page. Going to practice the right hand rule and the left hand rule. So now what is the work done by the magnetic force? The relationship or the expression that defines the work is the same force dot d, force dot the displacement. So the displacement here can be written as a function of the velocity. So d equals to v velocity times the delta t, which means the velocity here is into the expression, and we always know that for the case of the magnetic force, the force is always perpendicular on the plane that has the velocity and the magnetic field, which means that the angle between the force and the velocity is always 90 degrees in case of the magnetic force. And that's why if you take now the dot product between those two vectors that are perpendicular on each other is going to give you cosine 90 degrees, and this is going to be zero. So the work done by the magnetic force on a moving charge is always zero. We know that the magnetic field does not change the speed of a moving charge. However, it can only affect the direction of the velocity. It will result into changing the direction of the velocity, not changing the velocity itself. So as long there is no change in the velocity, we have no change in the kinetic energy, which means that the work done is zero. So how does this happen? Now let's look at here, this case, we have a charge, a moving charge in this direction initially, coming in this direction. This is a positive charge, so we can use the right hand rule. Right, using the right hand rule, pointing the index finger toward the V, pointing the middle finger out of the page toward the magnetic field, you can see that the force would be pointing downward. So in this case, if I have a force pointing downward, perpendicular on this velocity, the charge is going to change its direction. As you can see, the V itself is not going to change. However, the direction of the motion is going to change, and this is going to result into a circular motion. Now let's look at this question here. We have an electron moves horizontally towards the screen. The electron moves along the path shown, the dashed line, because of a magnetic force caused by a magnetic field. In what direction does that magnetic field point? So as we can see here, the charge is an electron, and it is going deflecting upward, which means that there's a force applied on this charge that goes in this direction. So if we use the left hand rule, where we point the index toward the V, we point the thumb toward the direction of the force, then we can see that I have the magnetic field pointing out of the page. So the answer to this is D. So here we have two questions that those two questions you need to try on your own. Slide number 17 and slide number 18, and we will discuss them and solve them later on during the live session.